Okay, welcome everyone to this is the week 6 webinar. And hopefully you're not too tired because you just had a project to turn in a couple days ago. But I thought I'd talk about the plan today. It's a bit of a lighter day because there's no project to talk about. A little too early to talk about the project too. Probably next week I'll start talking about it a bit more. And then a lot the week after. So the plan, as always, I'll answer any questions that you might have. That's kind of what these are about, is so that we can have interaction, because otherwise you just watch a long video and that's it. And then we're going to move and talk about something very important, something that comes up a lot in lots of research, and that is confidence intervals. So confidence intervals are a big deal. You want to, you do a sample, and the idea is you can say, well, I got the sample mean, but how confident am I about the sample mean? Because your sample mean is almost never exactly the same as the population mean, but maybe it's close. And the confidence interval will say, well, we could be, like maybe 95% confident that it's like within 1%, or within a half meter, if that's what you're measuring, whatever you might be doing. And that's what confidence intervals are about. So what we had done, earlier is we would be able to say, here's our best guess, but what we weren't able to say is how good a guess we have. And now we'll really be able to talk about how good a guess we have. And this is used in a deep way. It's easy to find applications. It's used everywhere. So we'll talk about confidence interval for means, and hopefully at this point in class, you know what a mean is. And then we'll talk about confidence intervals for proportions. So the first one is for means. That's when you have quantitative data. And for proportions, that's when you have a survey question and it's a yes/no question. Okay, or it could be turned into a yes/no question. And we can talk about, what's the confidence interval for that. So that's the plan. And just note, and this is important, you really can't do this without a calculator. So pretty much, I don't think there's anything left in this whole course that can be done without a calculator, and pretty much a fancy calculator, so some kind of statistics calculator. And again, you want to use the one I've given. Don't use something else that's not made for this class, because it won't do you well. There's all kinds of errors that'll happen. Okay, if you think you can use tables, don't. Okay, just note, sometimes I'll read through the discussion post answers or the exam answers, and I'll see just weird ways of doing it that don't work out, and don't do that. So I'm showing you the way in the webinar, so make sure you pay attention. Okay, then we're going to do another big deal. So we have seen that to be able to use the central limit theorem to find out that you have an approximate normal distribution for the sampling distribution, you need to have over 30. But the problem is that just tells you can use a normal distribution. What if you want to have a really good close estimate, and you want to get that standard error really small so that you can be very confident that your sample mean is very close to the population mean? Then how big a sample size do you need? Okay, that's a lot deeper than just saying I want to be a normal distribution. You could have a normal distribution, but you have this like wide range of values that you could say it might be. And what you want is not such a wide range of values. So we're going to be talking about, if you have this goal of, let's say, doing, I don't know, salaries, and you want to be within $10 per year of the average salary, that we're going to have to survey a lot of people for that. Okay, most people don't care about $10 per year for an annual salary, but if you did for an average, then you get to survey a whole lot. Whereas if you were okay being off by 10,000, you don't have to survey nearly as many. Does that make sense? So kind of the better estimate you want, the higher sample size you're going to need. So we'll talk about how you get that sample size. And then we'll talk about sample size for proportion. So same idea. So if you want to be, let's say you did a survey, some political survey to find out the percentage of, I don't know, people that like Biden. Well, you don't want to be off by 20%. You probably don't need to be off by, you don't have to like be so close that you're within 0.5%, but maybe 1% or 2%. So how big a sample size do you need to have that proportion to be off maybe by no more than 2%? And that's, we'll see how to handle that and how to get a sample size for proportions. I want to give you a heads up about this. Pretty much from now on, a lot of what we're doing has long, wordy answers. So get used to it. One thing is we are in week 6. And what's important about the number 6 that we've had in this class, 3 times now of the importance.
The exam.
Yeah, 6 is an even number. 6 is an even number. And when you have an even number, that means that we have an exam. So in the exam, the last 2 problems, it turns out, will be a written exam question. And you're going to have to do a lot of writing. Okay, you're going to have to write full sentences and use kind of the verbiage that I talk about today. Does that make sense? Okay, so that's just a note. Expect the written problems to be on this chapter, because the last chapter didn't have a lot of written stuff, if you remember. It was more of just calculation. But this chapter has a lot of written stuff. So be ready to handle that written stuff and pay attention. And just like the other exams, if you don't follow my lead, what I'm asking you to do, then I take off points. So take notes, okay? And you can always rewatch this. This is always recorded and popped on YouTube. So this is doable. Any questions? Any questions? Okay, just a note in terms of my progress. Unlike I can go pretty fast in grading your regular assignments, but projects take longer. So I am not done grading all the projects yet. I'm actually done with, I just decided to do section 4 first, and then I'll do section 5 next. So it takes a long time because, some of these projects are 17 pages. I can't just read it in 5 minutes. So just know it does take time. So have a little patience. I do my best. I actually woke up at 5 in the morning this morning, and I did not quite nonstop, but pretty much until I had to get on my skis and get here to the college. I was grading and reading your projects, and I put in lots of notes. And for those who are the one who submitted it, make sure that you do, and I tell you in my notes, in the comments, to share it with your partners, but make sure you do share it, the document itself, not the comments on the outside, but on the paper itself. I put comments, on special sentences that should have been fixed or were great or whatever it might be. So make sure you share that with your partner or partners. Okay, that is important. And if 2 people submitted, which you weren't supposed to do, but if that happened, then I only put the comments on one of the submissions. Just takes too much time to double up the work, and then I wouldn't get your papers graded. So I put on one of the submissions and make sure you share to the other person who submitted. Okay, so just this time I just did section 4 first alphabetically, and then I'll do section 5 alphabetically starting probably this afternoon, and then tomorrow, and maybe Thursday, however long it takes me to get through all this. It takes me time. Any questions? Any questions? Okay, so I have a question for you, and you have to answer, but you don't have to answer honestly, but you have to put a number in. And Braulio, you're a student, so I'm going to you're not my student, but you're a student, so I'm going to let you put a number in too. And the question is, how old were you when you experienced your first passionate kiss? And by the way, our sample size is going to be very small, unfortunately. And the numbers will be public, but who wrote the numbers will not be public. So no one's going to know who you are. So you don't have to feel too bad about giving it. But put it in the chat box, and everyone needs to. And all four of you have to. That's required. Otherwise, I mean, 4 sample size is way too small, but that's as big as we can get right now. So I've got 2, but put it in. There's 2 more of you. I'm watching the chat box. Shouldn't take too long to type in a number. And by the way, passionate kiss, that means that, that was your girlfriend or boyfriend or whatever it might have been, but not your mom kissing you on the forehead. Okay, we got 3 in, 1 more. And again, if you've never had a kiss, put your age. And then maybe it'll happen before your next birthday. And if you don't feel comfortable, just give me a number that's reasonable. Don't say 180, because that can't happen. And don't say 1, because if that happened, then someone goes to jail and should go to jail. So I got 3, 1 more. Hopefully you're paying attention. I don't see you. Really hoping for more than just 3. This is one of those where we really need more people. All right, I can't wait forever, but I don't see your answer.
Hi, I'm here. Sorry about that, Professor.
Oh, good. Okay, answer this question, and you don't have to say it. You can put it in the chat box, which then it won't be public. How old were you when you experienced your first passionate kiss? And if you haven't had a passionate kiss, how old are you now? And if you don't feel comfortable, just give me a number that's reasonable. If you haven't had one, again, what is your age? But most people have kissed. And put it in the chat box. And again, this is not going to be made public. The numbers will be not who wrote what. So there's going to be numbers to people. Okay. Yeah, if you don't, that's true. There's direct message if you don't want to be public to the rest of your classmates. Okay, so let me just put in what we've got. So we have 15, 15, 12, and 17. Okay. First thing, very important, is do you think this is a unbiased study? No, this is about as bad as it gets, right? This is like as much of a convenient sampling as you could even imagine. So I want to give you a heads up. This is not an example of how good study works. I just wanted to use, your numbers because, that's what I've got here. So you would not do it this way. If you really wanted to find out average age of first passionate kiss for college students, then you would do some kind of maybe a stratified sample.
Your call is being recorded by Calibri.
Oh, looks like I'm being recorded. We're double recorded. So, so just note that this is a terrible sampling technique, but it's all we can do. Do you think the sample size is large enough to be able to use a normal distribution, for example? What do you think?
Yes.
Okay, absolutely not. Our sample size is
No.
4. This is a sample size of 4. What is the central limit theorem you need?
30.
Yeah, over 30, 31, remember.
Over 30.
Yeah, we're not even close, okay? Which means we have to assume that the average age of first kiss for college students is a normal distribution. And there's no reason to believe that. I have no idea what the distribution is. So I want to, give you a heads up about, we're violating all kinds of stuff, but I want to do this as an example because it's fun. Okay. I'll also let you know I've done this for over 25 years, and I've seen big changes. So I've actually noticed what's going on. We'll talk about regression analysis and towards the end of the class, and then you can actually talk about those changes and how to predict and stuff like that. And just for interest, it makes a big difference in the world. It changes the world, because if people have their first relationship older, they tend to have their first sex older, sexual encounter, and then they tend to have their first child older or don't have a child. And since in the last 25 years, there has been an extreme drop in the number of children born per woman. And that has changed society immensely. So it's one of the biggest society changes, and almost no one talks about it. It's a big, big deal in societal changes. You know me, I'm a statistician, so I look at all the statistics and huge differences in how societies are with lots of children versus not so many children. I'm not gonna get all the details because it's a statistics class, but I will let you know I have done the statistics to see the differences and look at definitely statistical strength, significance, we call it. Okay, so the next thing we want to do is now we're going to say, well, let's find the mean of this. Okay, so the mean of this, I can quickly copy and paste, although 4 numbers, that's not that hard to do. But let's go find the mean. If I go to, let's go to the calculator. And should be in here. Probably should have searched for it faster for me. There it is. I'm going to show you kind of the longer way of doing it, and then I'll show you the short way of doing it later. So if I go to one variable statistics, I look at these numbers. This is a sample of all students. So it's not a population standard. We want to sample and hit calculate. The mean is 14.75. Okay. So the standard deviation is 2.06 about. So let's write that out. Standard deviation, that's S, 2.06. N is ridiculously small, it's 4. The one nice thing about N being 4 is when I get the standard error, I can actually do it in my head. And that's very unusual, by the way, to be able to do it in your head. I hope you all can tell me in your head what the square root of 4 is. Yeah, it's 2. And remember the standard error formula. So the standard error is a standard deviation divided by the square root of the sample size. So that's 2.04 divided by 2, which is 1.02. Normally you got to use a calculator, but this was so easy. And that's not, just weird. Any questions on that? Okay, so standard error tells you how likely our mean is to be close to the population mean, how likely the sample mean is to be close to the population mean. Given that we have an unbiased, random sample, which we don't, but we're going to pretend on that one. Okay, so the nice thing about the standard error, it's pretty much 1. So that means that, we're kind of off by 1. But if we use, then we use the empirical rule. Okay, we're gonna pretend we have a normal distribution because, in the real world, you do bigger than 30 sample size always anyway. So you can use the empirical rule that tells you 95% of the data is within 2 standard deviations of the mean. Well, in this case, we're looking at the distribution of X bar. So there's a 95% chance that we're within 2 standard deviations of 14.75. Well, 2 standard deviations, that's 2 standard errors, around 2.04 if you really wanted to. Well, if I add and subtract 2.04, I get 12.71 and 16.79. And the empirical rule says 95% of the data lies in that area. Another way of saying it is we could be 95% confident that the population mean is somewhere between 12.71 and 16.79. Any questions on that? Okay, it was a lot of calculations, but we'll be doing it in slightly different ways, but I wanted to kind of show you how this works. It's really coming from an empirical rule. Any questions on this idea? Okay, again, terrible assumptions when you have a sample size of 4, but we'll do what we have to do on this one. Okay, in the real world, you would never say that because in the real world, you say, oh, I have a sample size of 4, I know nothing. But we're going to pretend. Any questions at all on this kind of example? Okay, just a note, by the way, as I said, I've been doing this for, over a quarter century, and I compare it with myself. So when I was, when I was a college student, if, I talked to my friends, or when I was, of age of first kiss, I was like one of my last of like anyone I know of all my friends to do a first passionate kiss. I was one of those nerdy kind of weird guys, I guess. Any guess on how old I was? I was like really old compared to anyone of my generation.
22.
Good guess. I was 13. Life was different then. And we had a whole lot more fun as young teenagers in an interesting, fun way, just to let you know. And I've been watching this. I've been watching this every year because I do this for all my stats classes, including the one yesterday, face to face, which everyone has to come. So I had a bigger sample size, and it was pretty close to the same as what you guys had in your mean. They were a little higher actually, but I've been watching this mean go up and up and up for decades and decades. So, and it's just interesting, it doesn't really affect me, but it does affect the world in a big way. Any questions on this? Okay, some kind of cool statistics. So the picture of confidence intervals is this. So what we have is a normal distribution. Again, normally you're going to have a large enough sample size, you really can show a normal distribution, and you don't have to say we're just making it up, because the central limit theorem, as long as you're over 30, you can draw this picture, right? And I'm going to put X bar in the middle. That's our best guess for the sample mean, because remember that the sample mean is an unbiased estimator. Remember that? So sample mean is an unbiased estimator. So I can put that in the center of my normal distribution. And then what I can do is I can say, I want to think about what my margin of error. You might have heard those words and not understood them, not even in this class, but just in life. You might have you heard the words margin of error before? Okay, it's one of those words that you hear and don't even like pay attention to because you're confused and you don't even want to stress about it. But now you need to know it. So we're going to choose a margin of error, and that's kind of how far off I want to be, how wide an interval I want to have in my estimate. So if I go left and right by that margin of error, and I draw that under the normal distribution, then I can say that the area under this curve, which is the probability of being within the margin of error, I can say I'm that % confident that this population mean is within the margin of error, is between X bar minus E and X bar plus E. There's a lot of letters here. Okay. We call the confidence level 1 minus alpha. And if you didn't know, by the way, this is the Greek letter alpha. So yeah, one of the things about math, if you do a lot of math, you learn a lot of Greek. Not words, but a lot of letters. Mathematicians tend to use a lot of letters. Don't get mad at me, by the way. This is it's what everyone in the world, I believe, uses. Can't tell every country, but everyone in America for sure. So they all use that alpha. And the 1 minus alpha, there's a reason to call it 1 minus alpha, but we won't understand the reason until next week. Instead of just like using one letter, we're going to use 1 minus alpha. And 1 minus alpha is called the confidence level, and I abbreviate it as CL, or the level of confidence. And the standard level of confidence is 95%. Okay, so standard level of confidence is 95%. Any guess on who decided on the standard? And the hint is it was in the 1930s. Who was like in charge of like everything you learned about? Anyone know? It's history. The New York Times. So the New York Times is, there's no internet, by the way. I think you all know there was no internet in the 1930s. So all they had was newspapers. They didn't have television or anything like that. They just had newspapers, and the New York Times was the newspaper. And they made the decision. So that's historically. And they decided that they wanted to make sure that when they published an article in their newspaper, that 95% of the time they're right. Okay, you can't be right all the time because you do a sample. The sample is you're never 100% sure that the sample is the same as is close to the population, but you can be 95% sure. But you have to define that close by the margin of error. Okay, so that's really important in terms of what we're doing this week is this confidence level. It's kind of like how confident you are that the population mean really is in this interval that you have right here between X minus margin of error and X plus the margin of error. And standard is 95%. Not everyone uses 95%. In fact, when I did some consulting work for our Forest Service here, they told me to do 90%. They said they don't have enough funding to have a big enough sample size to really have a 95% confidence interval, because then the margin of error will be too big and it won't be worth anything. So they told me to 90%. And hopefully you all know the saying, the boss is always right. They told me 90%, and I did 90%. So when I sent them information, I used 90%. So again, that happens. When do you think you might need to be 99% confident? When you just don't want to be wrong. Who might need that? Any thoughts? All right, if you don't know, medicine. Think about, let's suppose that you were doing some new acne medication, or you put some cream on your face, and you want to make sure that it doesn't give people cancer. Okay. Cancer, by the way, hopefully you all know, is a lot worse than acne. So you want to really, really, really be confident that you're not causing harm. Does that make sense? So that would be a case where you may need a much higher level of confidence when being wrong is going to kill people. Do you see that? If being wrong is just going to make your newspaper article wrong, 95% is your standard. Does that make sense? Social science. So psychology and sociology always use 95%. I don't think I've ever seen anything where they didn't. Political science also always 95%. That is the standard. Okay. Any questions on that? Okay, so again, the central limit theorem. The central limit theorem tells us that sigma sub x bar is sigma over root n, right? That's what I used in the example we just did. Okay. And we don't know sigma, right? We had a sample size of 4. I found S. I did not find sigma. And then I still divided S by 2 instead of sigma by 2. And no one complained. No one said you did it wrong. Well, it turns out that it actually isn't quite right. You don't quite get the same numbers if you use a normal distribution. This was found a long time ago, many, many decades ago. And they realized that they weren't getting it right 95% of the time. They're getting it right a little less, and that's not okay. So the person who figured it out, believe it or not, had a lot to do with beer, and that's what you're all thinking. It's all about beer, because the guy who figured it out was studying beer for a brewery and looking at confidence intervals for how good beer is, I guess. I don't know all the details, and realized that using the normal distribution didn't work. And he came up with a new distribution. He did 2 things. He worked for a brewery and he taught. So he named it after his students and called it the student's T distribution. And that's the distribution you use when you don't know the population standard deviation, which is most of the cases. Because if you do a sample, you're not going to know the population standard deviation. So you use a student's T distribution, not the normal distribution. It looks pretty similar, and if you have a large sample size, it's almost the same. If a sample size of 4, it looks very different, actually. But a sample size of like 100, you can't even tell the difference. Just that, the bigger the sample size, the closer it is to a normal distribution. Okay, so what I want to do now is I want to show you how to interpret our interval. So we want to find a 95% confidence interval for the age of first kiss among adults involved in stats classes. So the first thing I'm going to do, by the way, I did this, and I kind of guessed at a confidence interval by using the empirical rule, but I could do better. I need to do differently because of as I mentioned, the student's T distribution changes things a bit. So I'm going to go to the calculator, and I'm not going to go to one variable stats. I'm going to go to confidence interval for a mean with data. It asks us to put the data in separated by commas. Okay. So I put the data in separated by commas. And this is definitely social science. How old were you when you had your first kiss? Is very social science. So I'm going to use 95%. Okay, so 0.95. For the confidence level. I tried to make this really easy to use. Did that look easy? Okay, and copy paste works, by the way, that's what I did. But sometimes you have to type it in if you don't have it somewhere else. And hit calculate. Okay. So the upper and lower bound are actually wider because, again, we can't really use a normal distribution. So it actually is wider than we thought. And it's really about 11.5 to 18. Okay. By the way, do you think this is okay to have a interval between 11.5 and 18 for the average age of first kiss? Yeah, no, this is terrible because it gives us no information. We knew this before we even asked the question. I hope you knew it. Somewhere between 11.5 and 18 is when people get their first kiss on average. We all know that. So we didn't even need to do it. So one of the problems is that our big problem is the sample size is too small. If we had a large sample size, we would decrease that margin of error. Okay. By the way, if we went to a 90% confidence, that will also decrease the margin of error. Oops, calculate, there we go. Then you get 12.3 to 17.2. That also decreased it. So I want to let you know, now that didn't take any work, right? I just changed the confidence level. So So why don't I just use a 90% and then I can get that narrower bound and I know, I know more. Do you see anyone see the reason why there's a problem with doing that? It's not always the best thing to do. I can go to 80% if I wanted. Between 13.1 and 16.4. So what's wrong with that? Any thoughts? Not mathematically, there's nothing wrong, by the way. But why is it not always a good thing to do? Even though I got my lower and upper bound with a smaller margin of error. Anyone see it?
It's more of a lesser confidence.
Yeah. Now we only have an 80% confident. Are you okay with being wrong 20% of the time? With telling people things and making them believe it, and then 20% of the time you were just wrong?
No, you would like to be closest to 100% possible.
Exactly. But if we went to 99%, let's try that. Now we're between 8.7 and 20.8. And yeah, now we're really confident that it's between these numbers, but we haven't learned anything because of course it's between those numbers. On average, people have a first kiss between 8.7 years old and 20.8. So it's a trade-off. Whereas if you want a narrower, lower to upper bound, so a smaller margin of error, and you want to be 99% confident, what do you have to do?
Get more data.
Yeah, you got to survey a whole lot of people. You may have to survey 1,000 people to do that. Do you see? So there's all these trade-offs, and I want you to understand the trade-offs. So, I quiz you on them. Okay, it's important to understand. See, and you can't have everything because good luck trying to survey 10,000 people. Nobody has that time, right? So again, you have to decide what's going to work for the amount of time and money you have and how willing you are to be wrong, because that's what this confidence level is, and what kind of bounds you need. Okay, what margin of error do you need? Any questions on this? Okay, so now let's go and I want to interpret the confidence interval. So what does it mean to be 95% confident? So let me write it out. With 95% confidence, the population mean age of first passionate kiss is between, and now let's go back and get it, 11.5 and 18.0. Years old. Any questions on that? Okay, just note, I want to put this in red. Do you know what it means if I put something in red?
Nope.
It means that you have to put it in there when I ask you to interpret the confidence interval for a population mean. Okay, those words have to be there. You have to refer to the population. Okay, we're 100% confident about the sample mean, but for the population mean, that's what we're interested in. And that's what we're 95% confident for. If it helps, I made a little conclusion template. So with XXX% confidence, it can be concluded that the population mean XXXXX. So in this case, it was age of first passionate kiss, but all depends on what you're researching, is between something and something. So the X's mean, don't put X's there, please. It means that this is a template, and then you just got to fill it in the context of the survey. Any questions on the conclusion template? Okay, so let's interpret the confidence level. Okay. So if we want to look at the confidence level, that's over here. Let me explain what that means. So our confidence level in this case is 95%, right? And that's actually a probability. And I like to think about it, kind of imagining myself as in the business of doing surveys. And the idea is every time I do a survey, every time I conduct a survey, I'm going to pop it in the calculator and I'm going to get a confidence interval, right? And the confidence interval, what our example was 11.5 to 18.0. Do we know that the population mean age of first kiss for college students is between 11.5 and 18.0? Is that true? Is it true that that is the population mean age? It's between those numbers. Is it true?
No,
So the answer is tricky. Maybe.
maybe.
Maybe it might be true and it might not be true. So I like to think about it as, here we go, we got a confidence interval. And if it is true, if it really is between 11.5 and 18.0, then we celebrate, we say we got it, right? Whereas if it isn't, we say, oh crap, we screwed up. We didn't get it. We told the whole world about something and we were wrong. Do you see? It doesn't mean we did anything wrong, right? We just got unlucky in the people we asked. Do you see? And so what the 95% is that every time you do one of these, you might be wrong, you might be right. But 95% of the time, you're going to be right. So 95% of all of the confidence intervals that you could do are going to contain that true population mean, and the 5% are not. And then you misled everyone. Do you see? So let's write that out. So what we can say is that if many studies of, let me make the font bigger so you can see it better. Our sample size was 4, okay, which is terrible sample size, but that's what we got. 4 students were performed, or were done. Then each would end up producing its own different confidence interval. If I ask 4 different students, I'm going to get a different confidence interval. Does that make sense? And if I went and asked a different group before, another different group before, I'll get a different confidence interval because they're going to have different answers, right? Okay. But what I can say is 95% of these confidence intervals will contain the population mean age of first kiss, while 5% won't. Any questions on the wording here? Any questions? Okay, so I made a little template. If many samples of XXX, in this case 4, but it's not always going to be 4, are taken, then each would produce its own confidence interval. XXX% of these confidence intervals will contain the true population mean of whatever, in our case, it was average age of first kiss, and whatever percent won't contain the true population mean. Any questions at all on interpreting the level? Okay, just to note, interpreting the confidence interval is more important than interpreting the level, because the level is like a technical piece. It's nice to know, but the interval, if you don't understand the interval, then the confidence interval is meaningless for you. Do you see? If you don't understand the level, it just means you got to trust the person, which is sometimes okay, sometimes not. Depends on the person, right? Okay, and then I want to give you a note. If you don't know the population distribution is normal, then you have to have a sample size of over 30. And that's central limit theorem. That comes from central limit theorem, because we use that. I will let you know the t distribution is an extension of the normal distribution and is absolutely brutal mathematically. So even if you have 2 full years of calculus, you will have no idea about the t distribution and how it works. It is really brutal. So just trust me that there is such a thing. Sound good? The equation, I can't even write on a page. That's how brutal it is. Normal distribution is tough, but nothing like the t. So it gets weird. All right, so now let's do the same thing, but let's do it with a thinking about the yes/no answer. Okay, so with the yes/no, with yes/no answer, it's a bit different because the central limit theorem looks different, right? So you can get different numbers, you can have different wording because you're not going to use the word mean. You're going to use proportion. Does that make sense? And I thought I'd give you a real life one in the news. And I like Gallup because they actually will show you the same stuff I talk about in their news articles. So that's why I use them a lot. So what percent of Americans are satisfied with the US abortion policies? Okay, so they did a survey. Okay, and they're never going to know the percent of all Americans that are satisfied. How come? How do they know they don't know the percent of all Americans? Any thoughts?
There's too many Americans.
Yeah, they didn't survey. Yeah, I know they did not survey them all. How do I know they did not survey them all? It's
So
obvious.
not everybody votes.
They didn't ask me. They didn't ask me, so I know they didn't survey them all. That's proof, right? By the way, did they ask any of you? I never had a student say yes, but one of these days, I'll have a student say, "Yeah, I was called and I answered the question." I've never had that happen. So again, all you could do is get a confidence interval. Okay, and by the way, if you go to their site, here's their site. It's kind of news, but they do it by surveys. And its dissatisfaction with US abortion policy hits another high. People are not happy with the abortion policy. By the way, I try not to get political. I do want you to understand politics though. Do you see? I'm not going to tell you how to vote or which side you should be on, anything like that. But I do tell you that it's a good idea to understand how it works. That I can tell you. Okay. So I just grabbed their first one, and that is 26% of US adults are satisfied. I don't think somebody turned on the, let me turn it off. Someone turned on the writing instrument. Let's see if this works. I think there's a clear all. Clear. All drawings. There we go. Okay, so 26% were satisfied. I want to scroll down to the bottom, and often these places will put it at the bottom because most people don't want to read it, so they put it at the bottom. And I click on survey methods. Okay, so not only do they put it at the bottom, they put it on the bottom, they hide it. You have to click to see it. Okay, and it says results for this Gallup poll are based on telephone interviews conducted January 2nd through the 22nd, 2023. This is a pretty new study, right? This isn't like ancient. With a random sample of 1,011 adults, guarantee it's not perfectly random. They probably use random phone numbers, but they have voluntary response bias. Again, that's chapter 1 stuff, but still important. Aged 18 and older, hopefully you all understand why they didn't ask people under 18. Because they didn't want to get sued either. Since you turned in your project, so you know. Okay. And living in all 50 US states and DC. For results based on total sample of national adults, the margin of sampling error is plus or minus 4 percentage points with a confidence level of 95%. So we could be 95% with 95% confidence. The population proportion, it's a yes/no survey question, right? Are you satisfied with the government's handling of abortion, right? Policy. So with 95% confidence, the population proportion of all Americans who are satisfied with the government's handling of abortion policies is somewhere between, and now we can subtract 4% from the 26%, you get 22%, and you can add, and you get 30%, somewhere between 22 and 30% of all Americans. Any questions on that? Okay. And just to note, it does say all margins of sampling error included computed design effects for weighting. That is kind of a process that's similar to stratified sampling, but I'm not. This isn't advanced statistics, so that's as far as I can get in terms of talking to you guys. Okay, so just trust me on it. Sound good? Okay. I don't need to read all the rest, but this is pretty important. Okay, because what we're doing. Okay, should we check to see if they got it right? Let's check. Okay, we have 1,011 adults and 46% said yes. So I'm going to go, this calculator won't work. How come? The calculator I just used, why will this not work?
There's not a list of data numbers.
There's not a list of data numbers, and there's a bigger reason. That's one reason, but there's a bigger reason. This is a quantitative study, not a yes/no survey question. Okay, this only works for quantitative. So, as hopefully you're used to by now, if it's important and we need it, I made a calculator for it, just not that one. So let's see if you can guess, what calculator number do you think I might use? Let's see it. Okay, we're going to do a confidence interval for a proportion. It's a yes/no question, so we're talking proportions. Okay, our N was 1,011. Our X, we have to actually do a little work to get X, not hard work, but 26% said yes. So we're going to take 1,011 times 0.26 and round to the nearest whole number, and that gives you 263 people said yes. Any questions on that? Confidence level, 95%. And I hit calculate. And the lower bound is 0.23. The upper bound is about 0.29. So actually, the margin of error is not 4%. Margin of error is 3%. Because remember, our p hat was 0.26. It actually reminds us of that. And if you take 0.26 and subtract 0.03, you get 0.23. And if you add, you get 0.29. And rounded, that's what we're looking at. So actually, they're off by 1%. Gallup tends to do that, and maybe I should call them one day. They always seem to get their margin of error off by a little bit. So they underestimate the idea of how strong their results are. Maybe because they're afraid of people getting upset if they're wrong or something, and they can say, "Well, see, our margin of error was high." But that's the upper and lower bound. Any questions on that? So we could say with 95% confidence, between 23% and 29% of all Americans are satisfied or happy with the United States abortion policy. Any questions on that? Okay, and by the way, if you're a politician, is that a good thing or a bad thing? Is this something that needs to be changed or not? Yeah, if only 26%-ish of Americans are okay with what's going on, that's not good. It means most people don't like it. So probably needs to be changed. And again, I'm not going to get into how, because that's politics. But I will tell you that, that's how you read low numbers like that. That means that, there's a lot of discontent, and it's not a good thing to have a lot of discontent. You want people to be happy with America. Any questions on this idea? Okay, so now let's go to the next type of example. Okay, let's suppose you wanted to find a 95% confidence interval for the population mean hourly wage of nurses in California. Okay, that's what you might be interested in. Okay, maybe you want to be a nurse, or maybe you're a HR director of a hospital and you want to find out how much to pay the nurses, however it might be. Okay, based on a preliminary study. Okay, so maybe you surveyed 10 people or something, nurses. The standard deviation is assumed to be $25 an hour. If you want a margin of error of no more than 50 cents, how many nurses must you survey? Any questions on the question? Okay, so just a note, and maybe I'll pop it in. Maybe I had it somewhere. Yeah, there it is. So we know that the margin of error is your standard error times Z. Okay, so Z is a Z-score for that level of confidence. So for 95% confidence, Z is around 2. Because remember, 95% of the normal distribution is within 2 standard deviations of the mean. So that's your Z. Okay, whereas if it was, say, a 99% confidence, then Z would be around, so for 99.7%, be around 3. If it was a 90, do you see how that works? Okay, but you can use the normal distribution calculator if you really wanted to, but I'm not going to. Okay, but sigma sub x bar is sigma over root n. So we get Z sigma over root n, okay, is equal to E. And then you do algebra. You don't have to do it, but you can trust me, I did it. Sound good? And I got that n is equal to Z sigma over E quantity squared. And that is a sample size needed when you know the level of confidence that you want, you know the standard deviation, and you know the margin of error that you want. Okay. Just a note, most classes in the state use this formula. I don't. And actually, some instructors got mad at me. Do you know what they got mad at me for? For creating the calculator that just makes it so they could do it without knowing the formula. So if you're mad at me, then you're allowed to use the formula, but why would you want to? Because I try to make it so that you're not stuck on all the, messy math. That really want you to interpret things well and understand what the results are. So we can now go and answer this question. And I'm not going to do it with the messy math. I'm going to go back to the calculator menu. And what calculator do you think I need? What number? Any thoughts? So put in the chat box or say it if you have an idea. Off mute, of course. Any thoughts? We're at number 11. If we want a sample size, how many do you need to survey? That's the sample size. It's not a yes, no question. It's quantitative, right? How much does that nurse make? So it's a sample size for the mean. So now we go ahead and here our standard deviation is $25. And our margin of error that we wanted was 50 cents, 0.5. The confidence level, we wanted 95%. So I'm going to go 0.95. And hit calculate N. Okay, so this says you need to survey 9,604 nurses. This is important because you do this and you might look at this and say, okay, I can't do this study. I don't have time. I know I don't. Maybe you have time to find 9,604 representative nurses in America and survey them for their salaries. Good luck. Do you see that? So this is one of those you say, well, maybe I need to let my margin of error be a little bigger because I'm just being too greedy. Or maybe I'll go for 90% confidence level. Sigma, you can't change. You can't say, well, I'm going to let standard deviation be different. The standard deviation is a given. You can't say, I'm going to change that, but you can change these guys. Any questions on this? And that's it. So we need to survey 9,604 nurses. Okay. Okay, if you wanted your margin of error instead to be, let's say, $2, you only have to survey 601 nurses. That might be, it's still a lot of work, but not as bad. Do you see how big a difference that is? Okay, so now you can also talk about a sample size needed for a confidence interval for a population and proportion. Okay. And there's two cases on this one. It turns out that for a mean, if you don't know the standard deviation, you can't do it. You can't get a sample size if you have no idea what the standard deviation is. So either you do a preliminary study, which means you might ask 20 nurses, and just use that as your best guess for the standard deviation, or you do research to get an idea. But if you don't know what the standard deviation is, you cannot answer the question. Does that make sense? Okay, it just can't be done. On the other hand, it turns out for a proportion, you don't have to know anything. You just have to decide what your confidence level needs to be, and you have to decide what your margin of error should be for you, whatever works for you, and you make that decision. Okay, so here's an example. Suppose you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. Sound like a nice study to do? So you want to figure out what proportion of cars are electric vehicles. And you could do California if you wanted, but whatever works. That's really important because if there's a whole lot of bunch of vehicles, we probably need to have more charging stations. We need to be prepared for more electricity, actually, and less gas. All those kind of things. So this is, something you might be interested in. Okay. If you want a margin of error of no more than 3%. 3%, by the way, is real common, by the way, for proportions, for margin of error. You'll see that a lot. There's a reason, and I'll show you in a bit. How many cars must you look at? Okay. Will this calculator work? Yeah, no, this is for means. This is for means. Ask for standard deviation, right? There's no standard deviation with proportions. So I need to go back to the calculator menu. Okay, and what calculator should I use? Good old lucky number. What calculator should I use?
12 or 13?
Yeah, 13. 13. Good old lucky number. I was joking. So 13, not 12. 12 is to get the confidence interval. That's not what we want to do. We're doing a planning. We're not doing the confidence interval. We're deciding how many people we need to survey. We're doing a plan. Okay, and you have to do that plan. If you don't know how many people to survey, then what do? You just go ask forever? Or you ask 2 people and say that might be enough. So the first thing you have to do, and or one of the first things you have to do when you're doing any study is decide how many people you have to ask. You see? And you got to know that. If you don't know that, then you may have terrible data, or you may have totally wasted your time. Do you see? Because if you only needed 200 people and you asked 20,000, you completely wasted your time. Do you see how that works? So getting that sample size is absolutely necessary in any study. Okay, it has to happen. But the good news is we can do it now. Okay, so I'm going to go sample size for a proportion. And here I put in little radio buttons. No estimate for P or have an estimate for P. Do we have an estimate for the proportion of EV vehicles in the United States based on the question? Okay, the question didn't talk about it at all, right? It just said, here's the margin of error we want, and we want a 99% confidence interval, right? We don't have any idea what percent. So if you have no idea what percent, then you click on the no estimate for P. Okay, then we read the question again. We want a margin of error of no more than 3%. So I'm going to go 3%. Don't forget, you always have to know how to turn percents into decimals. It's one of the few things in math you have to know for this class. And that's, if you get that wrong, it's going to be a disaster for you, by the way, pretty much for everything we do from now on. So we're going to go 0.03. That's the percent. Okay, confidence level we wanted was 0.99. And hit calculate N. So we need to ask 1,844 people. Okay, or we need to look at 1,844 cars. You could look at it that way too. Any questions on that? By the way, if you said that's too many, what might you change?
You could change E or the confidence level.
Yeah, you could change E or the confidence level. If you can change the confidence level, what might you change it to? This is one of those, you really need to be 99% confident. No one's going to die on this one. So what can we change it to?
Like 80?
You can do 80, but let's go standard. How about 95%? Because that's what everyone expects. Do you see? And you'll notice you get a little over 1,000. Okay. And I do want to let you know that this is kind of the standard. 3% for margin of error, 95% for the confidence level. And that gives us a little more than 1,000 for the sample size. By the way, would you have been okay with your project one had I told you have to survey more than 1,000 people? Okay, I hope you have better things to do with your life. Okay, so that's why in project two, and by the way, in project two, a big piece of it, any guess on what you're going to have to do for project two? Now that project one is over?
Find the sample size?
You can define a sample size, not really. You can define the confidence interval.
Okay.
It wasn't supposed to be a trick question. That's what we've been spending like the whole time on. So we're going to find the confidence interval. So for project two, you're going to have to do a confidence interval. We're not ready yet because it's not for a single population, it turns out. Or if not for one data, it turns out one data set. Turns out it's going to be two data sets, but we're not there yet. So we're not quite ready to even go there. But I give you hints about project two now. And you're going to have to find a confidence interval, and you're going to have to explore. You're going to have to say, well, if you want a 95%, then you can get your confidence interval. And if you want a 99, you're going to get a different one. And you have to decide which one to do. Okay. And it's very easy to look at it because all you do is change the number, it'll give it to you, right? So it's a 5-second thing. It takes longer to write about, which you're going to have to do for project two. But you are going to be required to change the confidence level and look at it and decide which one works best for your client. Same as project one, you're going to have a client. It'll probably be a different client, but same idea. Any questions at all on this example? Okay, so now comes the next one. And that's part B. So part B says, if you look at last year's data, 2.2% of all cars are EV. I looked this up. Okay. Okay. And I think I looked it up a couple months ago. So it's actually 2 years ago data. How many cars would you need to look at for the 99% confidence interval? Okay. How is part A different than part B?
There's no margin of error.
No, we're using the same margin of error, no more than 3%. So that should be pretty obvious. We know last year's data. So we have an estimate for the population proportion. Now, we're not saying this year is exactly the same as last year, but at least we have a first guess. Do you see that? So if you have a first guess or an estimate, that changes things a lot. So let's play around. Let me go back to the 99% because that's what we did in the last one. I want to show you how much it changes if we do have an estimate. So what do you think I have to do in the calculator to use my estimate of, again, 2.2%? What do you think I have to do? It's not a trick question.
You have to hit have estimate for P.
Yeah, I have to have estimate for P. So that wasn't a trick question, was it? So I click on have estimate for P. And you'll notice now it says, what is the estimate for P? And one thing you have to know how to do, again, very important, is how to take a percent and turn it into a decimal. What's 2.2% as a decimal? And a lot of people get this wrong. Again, it's basic math, but not everyone can do basic math. It's 2.2% as a decimal.
Point 0.02%?
0.022%.
Yeah,
Yeah, 0.022. Remember that we started out with the decimal right here, right? 2.2. And I move it to the left 2 places. That's how you do the mathematics of converting from percents to decimals, is you move the decimal over 2 places to the left, and that gives us 0.022. Any questions on that? Okay, so by the way, before we needed 1,844. That was when we didn't have an estimate. Should I click calculate N? Now you need 159. Huge difference. Huge difference. If you went and looked at 1,844 cars, that's a huge amount of work. Okay. Whereas looking at 159 still is a little bit of work, but nothing like, what we had to do if you didn't have an estimate. Do you see? So often getting an estimate is a good idea. And sometimes what you do is you might survey, you might look at maybe 50 cars and just use that as your estimate. And call that your first 50 in your sample size. Do you see? Look to see what you got and then calculate how many you need. Do you see? And if you get 2.2%, it'll turn it into 159 and then you go and survey 159. Any questions at all on calculating the sample size for a proportion? Okay, so as I mentioned, this is a bit of a lighter week. Okay, and it's a lighter week for 2 reasons. One, you have an exam. So that always gives you a little more stress, right? And the other reason why this is a lighter week is you just did your project, so you're probably tired. So I try to let you relax a little bit more. So we're done, except you need a secret word. And the secret word is with. And anyone know why it's with? Look at the template for a confidence interval interpret the confidence interval. What do you notice?
First word is with.
The first word is with. So it gets you started. And getting started is important. Don't you agree? If you get started, it's a lot easier to get finished. If you don't know how to get started, good luck. So the word with will get you started for interpreting the confidence interval. By the way, if I ask you to interpret the confidence interval, do not give me this stuff. This is for the level. So if I say interpret the confidence interval, I'm looking for this one. Whereas a level is this one. So get those, because they sound similar. They're not the same. They're very different. So that is pretty much it in terms of what I have to say. I am going to stop the recording because I don't have anything more new to talk about.